The last thing we want to do in regard to thermochemistry is we want to understand how all the different variables link together. So we talked about calculating the change in free energy, and that is equal to the change in enthalpy minus temperature, change in entropy under standard conditions, 1 atmospheric pressure, 25 degrees Celsius. We said previously in regard to these terms, delta G is going to be the change in, so all of this will be delta change in free energy, the energy available to do work, the change in enthalpy, measure of heat content of the system at constant pressure, T for temperature, and then delta S, the change in entropy. What I want to make sure is clear is when delta G is negative, the reaction is thermodynamically favorable. When it's positive, it would be thermodynamically unfavorable. When enthalpy is negative, the reaction is exothermic. When it's positive, it's endothermic, absorption of heat versus release of heat. And entropy deals with disorder. And when it's negative, the system is going toward order. And when it's positive, the system is going toward disorder. And we talked about entropy the other day. And we said, for example, order would be when you're going from gas to liquid, liquid to solid, or if you have all gaseous entities for reactants and products, if you're going to decrease the number of moles of gas in the reaction, that would illustrate order. We said that babysitting example, it's easier to babysit 2 kids than 3. With disorder, this would be, for example, solid to liquid, liquid to gas, where you're getting more disordered. Also, an increase in the number of moles of gaseous substances. So going from maybe 2 moles of gaseous reactant to 5 moles of gaseous product. The best combination you want for a thermodynamically favorable reaction is an exothermic reaction that illustrates disorder. On the flip side there, any reaction that is both endothermic and ordered will never be thermodynamically favorable. And we can diagram that out with a simple analysis of this formula. And if you understand algebra, it'll be very simple for you. For example, this equation right here, if you have an exothermic reaction with a negative delta H, and you have a reaction that illustrates disorder, a negative minus a positive will always, always, always give rise to a negative delta G, and therefore the reaction would be thermodynamically favorable. Always. On the flip side, if you have an endothermic reaction with a positive delta H and a reaction that illustrates order, maybe you are going from liquid to solid, or if you have all gaseous substances, you are decreasing the number of moles from reactant to product looking at stoichiometric coefficients. A positive minus a negative will always, always, always give rise to a positive, and that is indicative of a thermodynamically unfavorable or non-spontaneous reaction. So those combinations will be obvious to you. It can get a little tricky-wicky. You're very strong in math, so I feel confident you'll grasp this. The question arises, well, what happens, and I'm going to rewrite this here so it's a little bit closer. If you have an exothermic reaction that illustrates order, you have a negative minus a negative. If you want thermodynamic favorability, delta G has to be negative. So which term do you want to predominate? The enthalpy or the entropy? This one. And the way you will get this to predominate is with low temperature. At low temperature, the enthalpy term will predominate. And you can get thermodynamic favorability with an exothermic reaction that illustrates order. In contrast, if you have an endothermic reaction that illustrates disorder, if you want a thermodynamically favorable reaction with a negative delta G, would you want low or high temperature? You would want high temperature. So at high temperature, the entropy term will predominate. At low temperature, the enthalpy term will predominate. And that is far trickier. That would really be something very difficult at your level now. But certainly understanding that an exothermic reaction that illustrates disorder will always be thermodynamically favorable, and an endothermic reaction that illustrates order will never be thermodynamically favorable should be something that you can do. And this is all written out in words in your notes. I'm very math oriented, so I really prefer this type of interpretation here. I think it's easier for me. I also think having some type of chart here helps me organize the thought process here. But truly, in finishing out the chapter, you want to understand how enthalpy, temperature, and entropy together determine thermodynamic favorability, which is determined by delta G. And that will close out your thermodynamic chapter. In regard to your test, you want to make sure you're very comfortable with this concept. This is something that was not on your quiz. You want to make sure you're comfortable with Hess's law. That was something that wasn't assessed on your quiz either. So in preparing for exam 4-1, you really want to go over your thermo chapter. I would look through my notes. I would look at classwork 4.1 and 4.1s. You will be completing classwork 4.1 today. It's done through number 12 already, so you'll finish off the other problems. This is the one on Hess's law. That should be done already. I will return this quiz to you today so that you've got it to study from, but make sure you're comfortable with determination of Q using MC delta T. Make sure you're comfortable with determination of Q when you're either melting or freezing, boiling or condensing. Make sure you're comfortable with calorimetry. Know that the heat gained is equal to the heat lost. They're equal but opposite in sign. Heat gained is positive, heat lost is negative. You want to know how to calculate delta H for the reaction. You know that it is the delta H's of formation of the products, taking into account moles for each, minus the sum of the delta H's of formation of the reactants. And again, you do need to take moles into account because it's an extensive property. And then finally, you want to not only be able to interpret exo versus endo, but link enthalpy to entropy and temperature, and that's going to be through this formula here. But it's not enough to just plug and chug. You have to interpret. You have to know a negative delta G indicates thermodynamic favorability. You have to know a negative delta H is exothermic. You have to know positive delta S illustrates disorder. If you were given an equation such as this, does this reaction illustrate order or disorder, and why? This would illustrate order. Delta S would be positive or negative. Mommy, I want to go out at till 4 o'clock in the morning. What's she going to say? No, negative, order. Okay? So you want to be able to do that type of interpretation. Finishing off classwork 4.1 will help you with this. I gave you a ton of equations to analyze. It will help with better understanding of this as well, and that'll get you ready. If you don't finish your classwork today, you absolutely want to finish that tonight, and this way tomorrow night is when you are studying, not first getting a grasp of the material. That's important. All right, so that's thermodynamics. We talked about terms. We talked about heat transfer, enthalpy, entropy, free energy, how to interpret. And then in regard to calorimetry, that's what your lab was on. We can talk a little bit more about nutritional values of foods. Not something you're going to be assessed on, so I won't film. But it's something we certainly can talk about because it is important in everyday life. Questions?